Hello and welcome to another LeetCode problem. Today we're going to be doing the problem of the day for June 29th. Shortest path to get all keys. It's definitely going to be a very tricky problem, one of the harder problems of the days. And there are a lot of things you need to be using in here, and I definitely am using some things I've tried to stay away from, so I'm going to show you that here. Okay, so in this problem you're given an m by n grid where you can either have an empty cell like this, or a wall, or a starting point, or a key or a lock. So quite a lot of things. Lowercase letters represent keys, uppercase represents locks. And so if you walk over a key, you can pick it up. But if you cannot walk over a lock unless you have its corresponding key. And so there's only 6 keys though, which we're going to use. And they are the first K letters of the English alphabet. So there's 1 key for each lock, 1 lock for each key. And the letters used to represent the keys and locks were chosen in the same order in the English alphabet. We need to return the lowest number of moves to acquire all keys. This is impossible. Return -1. So for this first example, it's pretty straightforward, right? You can only go one way, then you go down, then you go left to open the lock, then you take that left key and you're done. So that's 1, 2, 3, 4, 5, 6, 7, 8 moves. Okay, let's take a look at the next one. So, and yeah, the goal is to obtain all keys and not open the locks. That's important. Like once we get the last key, we're done. We don't need to open every lock. Okay, so now we have one more example, and just looking at it, there's a couple ways you could do this, right? So one way would be you would go down here, get this key, and then you would have to come back and get the lock, but obviously that's longer than just going straight and then going down. So if you go straight and then go down, you would take this key, you would open this lock, and then you take this key. That's 1, 2, 3, 4, 5, 6. So that's going to be our answer there. And now obviously this one is pretty straightforward. There's a lock right in front of you and a key behind it, so you can't do anything. So this problem, if you haven't done problems like walls and gates, just pretty straightforward BFS problems, I'd strongly recommend you to do those. I'm going to link, I think I've done walls and gates maybe, or I'll link another BFS problem I've done, but you definitely need to be familiar with the BFS. And so let's just say we reworded our problem, right? Let's just say our problem was like so. So we had some cells and we're trying to get to like D destination from the start, and we have some walls. Like let's say this is all walls and we want to get to this destination. So you should be able to know how to do a problem like this if you want to do this problem, because if you can't do this one, there's like no chance. But pretty much you're going to do a BFS. So you're going to start at this node and you are going to mark nodes that you visited in some kind of set or hash map. And you are just going to add nodes that are next to it into your queue, and then as soon as you get a result, you're going to get this. So what's going to happen is like we're going to start here. We're going to add this into our visited set. Then we're going to move over here. We can try to go in all 4 directions. So if the nodes are out of bounds or if it's a wall, we can't add those. So there's only one viable direction, which is this one here. And so now let's just say this is visited. So by visited, you can also do some tricks, like you can say like instead of having a visited, you can just turn it into a wall once you were there. But whatever. So once you're at this node, you would BFS again, and you can only go in one way, right? So let's say we turn this into a wall. Now you can only go one way, right again, turn this into a wall. You can only go one way down, turn this into a wall. And you can only go one way down, and then we would get to our answer. And so at every single point, you would also keep track of a distance you've traveled. So let's say distance here is 0. At every single point, once you're adding the neighbors, you would just add the distance you traveled plus 1. That's how you do BFS, and you're pretty much guaranteed, because in these kinds of problems, every node is like one distance away. You can just do a breadth first search and you're guaranteed to get the answer, the fastest answer first. In a graph, it would be different because you can have 2 nodes that are connected, but you can have a huge distance between them, like 100, and then you can have a bunch of other nodes like this, you know, where like all of these would be like 1, 1, 1, 1, or whatever. And so you wouldn't just want to go to the closest node right away. But because in this problem, every single node is only one distance away, you can just take the closest node. And so if that happened in the graph, you could just take the closest nodes as well, right? Like if you had some connected nodes and you're trying to go from start to end, and every single node is one distance away, if it's all the same, you can do a BFS as well. Okay, with just a normal queue. So you would just pass all these nodes into a queue. Now we have some problems, right? And so what are the problems and how do we fix them? So one problem is like, let's draw this example now. So we have 3 levels, and we have 5 of these. And let's just figure out what the problems with a traditional BFS, right? Some problem with a traditional BFS is, let's say, what would be a good example here? Okay, so let's say we have a key here, and I'm just going to have a key here, so it's going to be K, and then we have a lock like this. Okay, so we're going to be going, right, in our BFS. We're going to be going. We're going to get to this node. And then let's say we visit the lock first, right? Like we're going to take the lock and the key. Let's say we visit the lock. Well, we can't actually open the lock, so we don't have a key. So in a traditional BFS, when you visit a node, you mark it as visited, and then we try to visit the key, and we'd say, okay, we have the key, but from the key, we can't go anywhere else because we've visited everything. So yeah, and so that's going to be a problem, right? Because we can actually go back. And so what we have to recognize, and this is going to be important, is once we get to a key, as soon as we get to a key, some lock opens, right? Some lock opens, and some lock anywhere could be somewhere where we couldn't visit before, but now we can. The lock can be here, the lock can be here, wherever it is though. As soon as we get this key, the lock opens, and so we have like a new grid essentially, because wherever the lock was, we can now visit. So we actually have to, whenever we get a key, we have to be able to try to visit every cell again. So every time we get a key, we're essentially resetting the state of the grid to where every single cell should now be allowed to be visited. So how do we do that? In a normal BFS, like I said, we have a visited set, right? So we have a visited set, and then we have like a row and column, and we fix that. So it's actually pretty straightforward how to do this. All we're going to need to do in our visited set is, or whatever you want to use, in visited hash map visited set, now instead of just row and column, we're going to have one more item called the key. And the key is going to represent the total number of keys we have so far. And I'm going to show you, it's a little tricky to do that, so I'm going to show you how that is. But now we can solve that problem where every time we get a key, so like for 0 keys, like if we, so let me actually draw this. So let's say black is our path with 0 keys. So we're going, you know, and let's say we go to this key. So now for black, all this is visited. And so for, you know, for all these rows, so for all these rows and columns, all of these, with key 0, they're all visited. So they're all true, or whatever you want to write it. They're all visited. But for all these same rows and columns with key, whatever this state key is, and we'll go into that later. So let's just call that K for now. Now those are not visited. So now we have a separate state for every time we pick up a key. And we actually have to, like, we can pick up keys in any different sequence. So if we have 6 keys, like, we have to represent all those combinations of keys in some way, right? So if we have keys 1, 2, 3, 4, 5, 6, we have to have this K represent all the combinations of all the keys we can have. So we can have like keys 1 and 2, keys 1 and 3, keys 4 and 5, keys 2, 3, 4, and so on. And so we can't just have K be like the number of keys that we have. We have to have K represent all the keys we have. And so I'm going to go into how we do that. So for this K, the way to actually represent the number of Ks that we have efficiently, and I saw this from the editorial, I think I had something else, but this is a better idea, is it's pretty straightforward. So one way you could do it technically is you could have just a bunch of like true falses or something, right? Where you could have literally like your K could be something like this, and then that just gives you more state. So this could be your K, where it's like some kind of tuple or something, and then the index represents like each key, and then you would just like toggle these on and off. That would be one way, but a more efficient way is actually to use bits. And so we're gonna have 6 bits for our K because we have 6 keys, and it's gonna be really nice to do this. So let's say we have 6 bits, so we just have these 6 bits, right? And then what we can do is we can just figure out, so these bits can actually correspond to the different letters. So like this will represent letter A, letter B, letter C, letter D, letter E, letter F. And all we have to do is once we pick up a key, we just have to figure out like what letter is it and what bit to toggle on. So like if this is our key, for example, and we pick up key B, we would just turn this B into a 1. And so we can represent this number as a 2. And let's say we pick up key D afterwards. We can turn this into a 1. And so what number is that? That's like 2, 4, 8. So this is 8 and this is 2, so this is like 10. And so that's how we're going to do it. We're just going to toggle these bits on. And because you only have 6 keys, actually the biggest number you can have is like 32 or something, right? So 2, 4, 8, 16, 32. And so the biggest number you can have here, right? 2, 4, 8. Yeah, so we can have like 32. So I think we can have something like 63 or 64 combinations, which is really cheap, right? So we're going to have a number for the key that's going to be 1, 2, 63, I think. And that's going to represent like what keys we hold. And so the way we're going to do that is, let me show you. So what we're going to do is we're going to have this keys. So we're going to have this thing. And then what you can actually do is we're going to use the ORed. And so what ORed does in Python is it gives you the ASCII value of a letter. So let's say we do like ORed of E. And we don't actually care what the ORed of E is, but what we do want to know is how far is that value relative to A. So if we do ORed E minus ORed A, ORed A is some value, and then we really care about what this difference is. Like we don't really care what this is and what this is exactly. I think this could be like 250 or 230 or whatever. But ORed E minus ORed A is essentially how many letters away is E from A, right? And so this would be, let's see. So imagine this is like a number, right? So this would be like 4 minus 0 and so on, right? So this would give you 4. And now we know, so now that we have this 4, and this we're always going to subtract ORed A to know like where our letter is from ORed A, because ORed A is the original, is like the first number. Okay, and then once we get this number, like ORed F would be 5 and whatever we get. Once we get this number, we're going to do something else. So we're going to have a number 1. It's going to look like this. So 1 looks like this. And we're going to shift our number, the number of bits that we calculated here. And so, for example, to shift it 4 times, it would go 1, 2, 3, 4. So this number would turn into a 1. So it would be a 0. And so now that we have our key, whatever key we have, we're always guaranteed to get like, there's only one of each key. So what we can actually do is we can AND the number we get with our key, and then that would turn on the bit that we want. So like here we got key E, because we shifted this one enough times, this would AND with this. And so this would AND like this. This bottom number would be this right here. And so you wouldn't AND them together, you would OR them together. And so when you OR a number together with another number, that means that this thing will stay the same, but whatever place this was in is going to turn into a 1. And so now our keys is going to, this 0 key will turn into a 1. So that's how you can like shift the bit that you want, right? And so we can easily figure out if our key is, if we picked up our key already, because we can just check for this bit. So the way to check if our key was picked up, we would do the same thing. We would do the shifting thing. We'd figure out where it is. And then if our key was picked up already, then I think we'd have to AND it together. Yeah. So if our key was picked up already when we AND these two, so the way AND works is if you AND a 1 and a 1, you would get a 1. And so if our key was picked up already, we would get some kind of non-zero answer. But if our key wasn't picked up, like for example, let me get rid of some of this. Like let's say all our keys stored is something like this, and our key is this. Our key is this. And now we're just checking, did we pick up this key? So when we actually AND these two, because there are no 1s that are both 1, this will give us a 0. So this will actually give us a 0. And so we could use these OReds to figure out if our key was picked up, and also when we do pick up the key, we can also change like our total number of keys stored. And so what we're actually going to do in the beginning, we're going to pre-process the data. We're going to take every single key and then figure out like what's its number and add those all together. And so the final result, like let's say we had every single key, right? Let's say we had key A through F. They were all in the grid. So our total keys, once we add everything up, would be this. Because essentially what we're doing is we're taking every key, we're moving it some number of bits, and we're adding all those together. And so then once so we have this like value for the total keys in the grid, and then we can just keep track of like what's the total of the keys we picked up so far, and if they're equal, then we know we picked up all the keys. So that would be a fast way to do it. You could do, like I said, you could do some other tricks where you have you have like an array, or you have some other thing, but this is like the fastest, I think. Plus, like I said, I never really used ORD before, so I think most people try to stay away from bit manipulation and ORD. So if you did try to stay away from that, I would encourage you to try it out just to like get comfortable with something you don't use very often. Okay, so now that we know that, we need to have a separate state for like every sequence of keys we pick up, because every key we pick up essentially unlocks a new grid. We know that, and then we know how to calculate directions, and we know how to do BFS. I think we have everything we need to do the problem, so let's look at the code, and if I miss something, I'll definitely explain that. Okay, so in the code here, what we need to do is, like I said, we're going to actually get a set. So the other thing we're going to do is we're going to have a set of all the keys in the locks, and these are just going to be like locations. And so the location is going to be, actually going to be here, just the value in the grid and the column. And so we're going to have all the keys and the locks in a set. And so that's quickly going to be able to tell us, like if we're at some key, we're going to be able to quickly tell, is that a key or a lock or whatever it is. And so this sum keys will be the sum of every single key we've looked at. And that's what we're going to compare. So that's going to be this thing on the left. When we go through every key and we move them over, and let me show you that. Yeah, so it's right here. Yeah. So pretty much you take a 1 and you shift it over this ORD location minus a, and then you add all those together. And these will be like unique sequences for unique numbers for every key. So when you did take every key and you add them together, that will be the sum keys, and we can do the same thing in our traversal. Every key we pick up, we can add this, and then once we pick up every key, it'll be equal to sum keys. And then the same thing for location. So if our location is in this, we're going to add the location. So our key is going to be a lowercase a through f. So we can just say in the beginning when we traverse, we just say like, if our key is a lowercase a through f, let's add that. And if our location is in this, you don't necessarily need it. Like you don't necessarily need the locks or keys if you don't want to. You can just manually ask yourself if it's an a or a lowercase a or whatever. Okay, and so now we need to make an actual. The other thing, by the way, that you need to see for this problem is you don't actually always start up here. It says this at is a starting point, so you do need to do a pre-process of the rows and the columns. And if we're doing that, then we might as well get all the locks and the keys and things, because we are, like, for all you know, we could be starting at the very end. So we have to do this beforehand anyway to figure out where we start. Okay. So now we're going to use a deck for a standard breadth first search. And what we're going to have is we're going to have a row, we're going to have a column, and then we're going to have this 0 is going to be like the total keys we have. And remember, it's not a number of keys, it's a bit mask of keys, and the distance of traveled, which is going to start at 0. And then we're just going to mark that at visited. And like I said, we're going to have a visited at a starting row and starting column. So that's pretty straightforward. And let me just make sure here. Yeah. Okay. Actually, this should be, this is actually not needed, I believe. I believe this is just wrong. Yeah, so I think this should just be visited starting row, starting column, and 0. Yeah. And then we're going to mark that as true, or whatever we're going to have that as. So it's actually, sorry, so in our visited, we're going to have, we're not going to have like true or false, we're actually going to have a value. But you can have a set if you want to. So I think this is what it needs to be. Okay, yeah. So yeah, so what you need to do is you need to initialize, and like I said, in our visited, we're going to have a row, a column, and a key. And so our key is going to start at 0, and we're going to say the distance, like the total distance for this exact thing is 0. But like I said, I think you can just have like a true or false as well. Like I don't think this needs to be a hash map. Okay, and so what we need to be doing is we need to be going through this deck, and we need to be going through every single. So typically, what you do in a breadth first search is you're just going through the deck until you have nothing left. And if you have nothing left, that means we couldn't get to our result. So we just return -1. And so what we're going to do is we're going to keep popping the row, the column, the keys, and the distance. And this is going to be our condition to determine if we're done. So the keys is, like I said, the bit mask of the keys that we have. And the sum keys is the actual, once you pick up every key, is what it should look like. And so this is pretty straightforward, like in my other videos. So you make a new row and new column in every direction. So you just have like a up, down, left, right. Pretty straightforward. And then we have our conditions for when we need to not do anything. So if we're out of bounds or if we're at a wall, we don't need to do anything. Now location is going to be the actual value in the row in the column. It's going to be a string. So one of these. And now what you need to do is you need to check if the location is in the keys. And if the location's in the keys, you need to actually check, like, have you seen this key before? And so what this does is this is saying, give me a new key. And so, like I said, every time you find the new key, so imagine you're going, you find the new key. As soon as you find the new key, you're in a new state. You don't really care about the old state anymore. We're just going to be updating with the new key state. Because as soon as we find the new key, some of these locks can magically open that we've already come across. And so pretty much what this is doing is if our location is in the keys, that means we haven't visited it yet, I'm pretty sure. Yeah, we haven't visited it yet. And what happens is we need to get a new key. And so yeah, so we check if it's not in visited. I don't think it should ever be in there, but I'm not entirely sure. And so yeah, so we get this new key state. And so in this case, like we pick up this first key, and if this first key was an A, let's say, then our new key state would be a 1 and it was a 0. Then if it wasn't in visited, what we need to actually do is we need to give it a distance, and then we can append it to the path, and we can continue. So if we get a new key, we need to append. Think about what we're appending, right? We're appending the new row, the new column. We're appending the new key state, and then we're appending the distance plus 1 from where we were. So like if we were here, right? If we were here, then that means the key, like that means we had to be here and the key was over here, because our new row and column only goes 1 in every direction. So we had to have been here, and then the key's here. And so how far is it from here to here? It's always going to be 1. So we append 1 and then we continue, because if we found a key, that means we're going to add that key into the deck, and we don't need to actually check for other stuff because this is like a separate case. Okay, so now we have another case, and the other case is if we hit a lock, but we don't have the key. So if we hit a lock and we don't have the key, it's pretty straightforward. We're just going to skip. It's the same thing as a wall, right? And then as soon as we pick up a key in the future, that lock might open, and that's why you have the new key state. So that's pretty much what it boils down to. This problem is pretty much a BFS, but you need to recognize you have a new state every time you open a key. You don't have a new state every time you open a lock, though. Like a lock, once you have the key for it, is just a normal cell. And so that's what we're doing here, though. If we have a lock but we don't have the key, and the way to check that is the same thing. Now we're subtracting the uppercase A because this lock is an uppercase letter, but it's pretty much the same thing, right? We only care about the difference between where it is and the uppercase A, like the distance between that. We don't care about this value. We don't care about this value. We only care about the difference. Okay, so now we finally have our last case, and our last case is we just hit some random cell. And that random cell can either be a lock that we have a key for or an open cell. And so in that case, you don't want to be repeating, right? That's the whole point of a BFS. So you don't want to be, like, if you haven't visited the cell, you only want to be doing stuff. But if you have visited the cell, you don't want to be doing stuff. Otherwise, you'll just go back and forth, right? You'll just go like here, 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 and it'll be an infinite loop. And so if we haven't visited it, then what we can do is we can say that we have visited it, and we can add it to the paths. And like I said, in a deck, as soon as you get to a cell that you didn't visit and you add it to the deck, because the distance between every cell here is 1, as soon as like you added a cell to the deck, you don't need to ever add it again, because there will never be a better reason to add it. Where, like I showed in that graph, that's definitely not the case for like a heap or something where your cells aren't all equidistant. So for a graph, if this was 100, right, and then this led somewhere else, let's say like this was our start, this was our end, and then these nodes were shorter, like this was 1, 1, 1. So like let's say our algorithm just took the nodes like near the node that we're at. So if we're at this node, we would add this node, and we would add this node, and then once we're at this node, we would add this node, and then once we're at this node, we definitely would want to add this node again, because this path is way shorter than this one here. But because here, everything is equidistant, if we already added a cell, then we don't need to add it again, because we're going to get there faster with the other way. And so that's why you can just safely add to visited right away. Where in, like I said, in a graph, you can only add things to visited once you actually pop them out of whatever data structure you have and you actually visited. You can't just add them when they're in the data structure. And so the final thing is when your deck is empty, that means you tried going all your paths, but you couldn't find anything. And so if you couldn't find anything, that's when you would just say that you can't. There is no path to get to the to get to all the keys. Okay. So I actually do want to try one thing. So I did have these distances, and I did have these distances, but I think we can just refactor this to not have distances at all. And so I think we can literally we can have this be a set, I'm pretty sure. And so let's see where we have visited here. So we can just say, yeah, I'm pretty sure we can just do that. So we can just add these values instead, because we don't really care about the number. So let's see where else we have it. Yeah, let's try it again. And a couple more, I think. Yeah. Okay. Let's see if we. No, right. Hopefully we don't have any more equals. Okay, let's take a look what happens. Oh, we actually do need double parentheses for these and double parentheses for these because we're adding a tuple. Okay. Okay, so that still runs. Yeah, so either one of those is fine. I think it runs a little bit faster now because we don't actually need the value. We just need to make sure that we have visited it or not. Okay. And so let's think of the time and space here. So like I said, imagine every time we hit a new key, we have a whole new grid that we can traverse. And so worst case scenario, you can imagine like you would pick up all the keys, but then for every path to every key, you would traverse most of the grid. What's that going to look like? Well, it's going to be m by n is the grid. And then how many total keys are there? So it's actually 2 to the 6th, I think. Yeah, I think it's either like 2 to the 6th or 2 to the 5th. I think it's like 64. So what's 64? It's like, so 4, 8, 16. Yeah, I think it's 2 to the 6th is what it is. Okay, so if you have 2 to the 6th keys, and then you have m by n for the grid, remember every time you find a new key, it's a new state. So you just have to figure out how many different combinations of keys can you pick up, and it's going to be 2 to the 6th. Because, yeah, and like I said, if you want to figure out what that is, so it's pretty much going to be if you have 6 different spaces for the one, right? So you have A through F, it's going to be whatever this is, and I think that's like 63. So this is the number of different combinations of keys you can have, and for every single different combinations of keys, you're going to open up different locks, and so that's going to be a new state. And so the number of time, like the total time for this would be m by n by. If you want to write it like this, you can write it like this as well. But k is quite a small number, and so you could technically, because this is only 64, you could technically say that's n by n. I think that would be a valid solution because the number of keys is so small. And that's what they're trying to get at here is like it's not costing you too much because there's not too many keys. Once the number of keys gets really big, also m and n are really small, right? So actually it's pretty easy to, I think it's pretty easy to pass this problem just because the parameters are so small. As long as I think they're mostly testing just like, can you figure this out? Because there's so many things, right? Like there's keys, there's locks, there's a BFS, there's a lot of things for sure. So they're trying to make it easy to pass, but not so easy to figure out what's going on. Okay, so for the space, pretty straightforward as well, right? So we have this visited set now. And so in the visited set, we're going to have the row, the column, and the key. And so row, column, and keys is also, like I said, 2 to the k. And if you wanted to argue that this is just constant, that's totally fine, I think. Okay, so that's going to be it for this problem. Definitely a challenging one. Definitely a lot to do. And Yeah, I was trying to stay away from the award. Like I said, I think you could definitely not use award. You could do something that takes up a little more, just because they're so generous with how much space and time they give you. If you don't want to do it, you don't have to. But I just wanted to show that here. Okay, that's going to be all for this video. If you liked it, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.